yet another sensing modality. The title is Headar, Sensing Head Gestures for Confirmation Dialogs on Smartwatches with Wearable Millimeter Wave Radar. It will be presented by Xiaoying. Is that true? Okay. Try the other one. This one we will not recognize. Try this one. It will not recognize the other one. It's classic Mac. That looks good. Yeah. Now we can do it.
Hello everyone, I'm Xiaoying. I am happy to present our work Headar using millimeter wave radar to detect head gestures on smartwatches. This work is done in collaboration with Wang, Gaofeng, Srivastava, and Zhang from UCLA, Zihan from MIT, and Eiji Hayashi from Google. To facilitate the small screen size of smartwatches, input options are usually narrowed down into two categories: accept or dismiss the recommended actions, which we refer to as confirmation dialogues. Confirmation dialogues have been widely used, such as accepting or dismissing a phone call, approving or denying a request, starting or stopping an alarm, resuming or ending a navigation. On the other hand, we notice that in daily conversations, people tend to nod or shake their head to show agreement or disagreement with each other. We are inspired to use these natural and intuitive head gestures to replace the touchscreen interactions on smartwatches. We use a millimeter wave radar to detect head gestures, which yield high-fidelity spatial information while preserving user privacy. By nodding or shaking, users could respond to smartwatches in a natural and efficient way. To validate the effectiveness of using millimeter wave radar to detect head gestures, we conducted simulations to synthesize radar responses to head gestures. Specifically, we generated 3D head meshes from 2D images using state-of-the-art and ready-to-use head alignment model. Then we defined head gestures by defining the orientation angles of these head meshes. We also modeled the radar with multiple antennas transmitting FMCW signals. In this way, we synthesize radar responses for nod and shake gestures, which have similar features to those of the measured signals for both gestures. When a user performs nodding, the head leans forward and backward and shows a negative and positive velocity sequentially from the perspective of radar. However, while shaking, the head rotates around the rest of the human body and has both positive and negative velocity at the same time. This is the source of the signals we leverage to differentiate the two head gestures in Headar. We then conducted 2 studies to investigate the characteristics of people performing head gestures and positioning smartwatches. Participants were instructed to nod, shake, and raise arms as naturally as possible, with markers on their head and wrist checked by the optic check cameras. We found that participants generally performed head gestures with less than 7 cycles within 2 seconds. Most participants head up to initiate nodding and head right to initiate shaking. The magnitude and speed of head gestures shows consistency within participants while great diversity among them. We also measure the distance, azimuth angle, and elevation angle between the smartwatch and the wearer's head. The azimuth angle showed the largest variance among participants, with watches positioned on both sides around the head axis. The simulations and studies informed us to choose the TIAWR 1843 radar sensor for head gesture detection. We configured the radar sensor carefully so that it has a field of view sensing range and resolution sufficient for capturing user head positions and movements. Our sensing pipeline includes wrist status detection, head gesture signal segmentation, existence detection, and inference. We employed an IMU sensor to detect whether users raise their wrist, a feature that has been effectively implemented in commercial smartwatches. Upon user raising their wrist, our sensing pipeline continuously monitors for potential head gesture signals. To address the challenges posed by random body movements, we incorporate a gesture existence detection layer to examine the variation of signals and extract positive sequence for gesture inference. Each frame of the sequence is processed with a frame model consisting of several residual block CNN layers and dense layers to extract spatial features, which are then concatenated and fed to an LSTM layer to integrate sequential information and then output the classification prediction. We conducted a user study with 15 participants in both sitting and walking scenarios, with participants performing 9 motions that people generally performed on smartwatches at the raise-to-speak positions. We ran a live one session out and live one user out validation to our model. The average detection accuracy is 85.5% and 82.5% respectively. However, in real-world uses, only the 2 gestures, nodding and shaking, can be considered as effective input, and other detected motions can be discarded. So we bundle the 7 labels on the confusion matrix, which result in an increased detection accuracy. We developed several example applications to demonstrate the use cases of Headar. All demos were powered by our real-time detection pipeline. For example, users could continue or stop navigation while driving using head gestures. Start or stop watch to keep track of exercises. Indicate they are safe for dismissing an emergency phone call. This is my advisor. Users could dismiss a phone call with a simple shake of their head when their hands are occupied. Finally, we discussed the limitations of our current sensing approach. Participants in our live test had to find the optimal head position and orientation for interacting with smartwatches. This user adaptation can be improved by careful design of the wearable radar sensor, signal processing algorithms, and deep learning models, and a larger and more diverse data set. Future investigations are needed to further the understanding of the impact of noise and body movements from vibratory environments on head gesture signals, and the utilization of IMU signals could mitigate this impact. We also envision future wearable radar systems to detect a wider array of head gestures and even precise head tracking to enable a richer set of applications. which may be realized by the improvement of antenna design and sensing resolutions. Thank you for listening. I'm happy to take questions.
Thank you very much. So, question. Okay, in the case, thanks a lot again. Please stay here for later question and discussion.
Okay, I have a live demo.
Yeah,
No,
that's a very,
I have a demo. Maybe we can discuss later. Yeah, thank you.
So we are through with the input paper. Now we have 2 remaining ISWC papers. Both ISWC papers are best node candidate for ISWC, so listen carefully. And we're back to Bo, who will be showing some more material on the capacitive body posture sensing.